So we're looking again at some more extensions to electron configurations. If you're following along at Fairfax, this is your page 11 in your Unit 4 binder. Okay, so what we're going to do is kind of clean up and talk about some of the remaining little things that we can do with our electron configurations. The first one we're going to talk about is called N notation. What this is a way to basically shorthand refer to an entire group on the periodic table. So we're going to start with the group of the alkali metals. Hydrogen has got a configuration of 1s1. Lithium, make this easy on us, it's got a configuration that looks like helium 2s1. Sodium looks like neon 3s1. And potassium looks like argon plus a single 4s electron. Now, what do we notice? Every single one of these ends in S1. Let's see if there's any pattern to the numbers. We take a look at our just the far left column of our periodic table here. We see hydrogen is in the first period, and it ends in 1s1. Lithium is in the second period, and it ends in 2s1. Sodium is in the third period, it ends in 3s1. Potassium in the fourth period, and it ends in 4s1. If we had to take a guess, what do you think cesium would be? And if you guessed 6s1, then you'd be correct. What that number means is the energy level of its outermost electron. Okay, the energy level. Okay, so if we want to refer to this group as a shorthand, what we can do is say that for any given period, that's what this N means, an atom in this group is going to have a configuration that ends in S1. Let's see a couple more just to make it clear. Write the N notation for group 2, so that would be, for example, beryllium, 1s2, 2s2, or magnesium, 1s2, 2s2, 2p6, 3s2. And if we go right on down the line, we'd see that each one of these in turn ends in some s2, ends in 2s2, ends in 3s2, ends in 4s2, ends in 5s2, ends in 6s2, ends in 7s2. For any given period, for any given energy level, this thing is going to end in s2 at that energy level. Okay, so N notation for group 2 would just be N for any given energy level, S2. Let's take a look at group 13 and 14 here. Okay, so group 13. Group 13 would be something like boron, 1s2, 2s2, 2p1, aluminum, let's go ahead and give you the abbreviated one, neon, 3s2, 3p1, and let's even look at gallium. It looks like argon, 4s2, 3d10, 4p1. Well, this guy ends in s2p1. This guy ends in s2p1. This guy ends in s2, 3d10, 4p1. Well, what if I also told you that the N notation only referred to valence electrons? In which case we can say, hey look, valence electrons are the ones at the highest energy levels, 4 and 4. 3D would not be a valence electron, so it's not going to get included in the N notation. They're still there, we're just not going to refer to them as such. So for group 13, boron in the second period, aluminum in the third period, gallium in the fourth period, they all end in N for that period, S2, N, P1. The pattern is actually going to continue across the entire P block. So if we take a look at the P block, to get to carbon, you've got to have 2 electrons in the P orbitals. So you've got your S2, P2. Nitrogen would be S2, P3. Oxygen would be S2, P4, S2, P5. Okay? And that's going to hold down the entire column. Okay? Anything in carbon's column is going to end in S2, P2. whatever that energy level is. Carbon is at 2, silicon ends in 3s2, 3p2. Germanium would end in 4s2, 4p2, obviously accepting all that d block stuff that we just did. So group 14 would end in ns2, np2. Group 15, we just build right across and we keep adding new electrons into the p orbitals. ns2, np3. Group 16, ns2, np4. We need a visual here. Group 13, 14, 15, 16, 17, and 18. We're just moving right across the p block. Okay? So group 17, the halogens, ns2, np5. Finally, group 18, ns2, np6. It's just a quick way of referring to an entire group by its valence electrons. Okay, so these are only the valence electrons, and they're actually going to give us a good count of how many valence electrons each individual group has. So let's go ahead and review a little bit of valence electrons here, just to make sure we're all on the same page. Valence electrons are located at the outermost or highest energy level. And we just look at the s and the p electrons at the highest energy level. Because if we use d, well, to get to the 3d, we already need to put something in the 4s. So wouldn't really make much sense. Electron configuration for beryllium: 1s2, 2s2. And circle the valence electrons. Those would be at the highest energy level. For nitrogen, 1s2, 2s2, 2p3. And circle its valence electrons at the highest energy level. I see 5 electrons at the second energy level, so they would all count. The N notation for nitrogen's group, well, let's take a look. Nitrogen's group is group 15. Okay, so we know that group 15 has the N notation of ns2, np3. Now, we could even have done that just by looking here. We know nitrogen is in the second period, so we know its N is going to be 2. We know it's going to be 2s2, 2p3. I see 2 plus 3. I see 5 electrons, which is exactly what we should have gotten, 5 valence electrons from group 15. That's right. So let's go ahead and finish this one out. Write the noble gas abbreviation for selenium. Selenium, being right here, we're going to zoom out so we can see the whole P block. Okay. Still not. There we go. So if we take a look here, okay, we'll try and zoom in a little bit more then. We take a look here at selenium, okay, at selenium. The noble gas that comes right before it is argon. Now we just have to build up to selenium. The next electron we put in would be the 4s2, 3d, 10, 4p, 1, 2, 3, 4. Okay, so it's going to look like argon, 4s2, 3d10, 4p4. Okay, zoom back in here so we can see this all good. Okay, now the valence electrons, we're going to circle its valence electrons again. 4 and 4. Those are both at the highest energy level. The 3d is not. So this would have 6 valence electrons. Since it makes sense, it's in group 16. Okay. How many valence electrons does vanadium have? Well, we haven't talked about the noble gas or the transition metals yet. So let's actually write this out. Vanadium looks like this: argon, 4s2, 3d3. Well, we know that the d electrons don't count towards valence electrons. We just look at the 4s. It's got 2 valence electrons. Tin, a couple different ways we can do it. We can look at tin, see it is in group 14, and know that group 14 has 4 valence electrons. We can also confirm it. Tin has an electron configuration that looks like krypton, 5s2, 4010, 5p2. We know the d electrons don't count, they're at a lower energy level. Here's 5p2, 5s2. Once again, we get 4 valence electrons. Okay, So now that we've done all this work with valence electrons, we're going to see how we can use it. All right? Valence electrons are going to be very important because they, again, predict how things are going to react. So let's see how we might represent that. Sodium comes from a group that has one valence electron. So to write a Lewis dot diagram, okay, which you can see dot diagrams or dot notation, what have you, each dot is going to represent a valence electron. Sodium has one valence electron, so sodium gets one dot. Magnesium has two valence electrons, so it gets two dots. Aluminum has three valence electrons, so it gets three dots. And notice it doesn't really matter where we put the dots. Sulfur has six valence electrons, so it's going to go 1, 2, 3, 4, and then start pairing up, 5 and 6. Chlorine has 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. Argon has 8. So each side would get a pair. That's all it is. Lewis dot diagrams, just one dot for each valence electron, and then put it around to make sure not to pair them until you absolutely have to. Flipping the page. Okay, we already talked a little bit about the ion configurations. Okay, so, sorry, this is how many electrons. Okay, you can use the abbreviated form if you like. Okay, so what we want to do, decide how many electrons this thing has. Chlorine started out with 17. It's got a -1 here, which means that it has gained 1 electron. It means it now has 18 electrons, and it looks like argon. Its electron configuration then would be 1s2, 2s2, 2p6, 3s2, 3p6, just like an atom of argon. Okay? It is chlorine, but it has an electron configuration like argon because it's gained the 1 electron. Phosphorus starts off with 15 electrons, and it's gained 3. So it too has 18. So it also looks like argon. Now, if we want to do this a little bit differently, let's do this with the noble gas abbreviation. Unfortunately, even though argon's a noble gas, you can't just say, oh, argon looks like argon, and put an AR in there. Can't do it. Let's go back to the one that comes before it, so neon, and then build it up from there. 3s2, 3p6. Calcium started off with 20 electrons. It's got a +2, which means it's lost 2 of them, and now it's got 18. Well, it's going to have the same electron configuration since it still looks like argon. Look at boron here. It starts off with 5 electrons, and at +3 charge, it's lost 3 of them, so it only has 2. It looks like helium, which has an electron configuration of 1s2. And that's it. Beryllium starts off with 4, and it's lost 2 to again have 2. So it also looks like helium with a 1s2 noble 1s2 electron configuration. Sulfur, the last one here. It starts off with 16 electrons, it has gained 2, now it has 18, so it looks like argon with, again, this electron configuration of neon 3s2, 3p6. The only other thing we're going to do is something that you don't need to know for our test, but if you're eventually going to go on to AP, then this is going to be good for you to know. There are exceptions to the electron configurations. Okay, we're going to shade in these guys as we learn it basically. Basically, it's better for an atom to have all of its subshells, so those are the S subshell, the P subshells, it's want to be completely filled. If that can't happen, they're going to try and fill them halfway. So let's, for example, look at copper. Copper, we would predict where it is on the periodic table, we'd predict it to end in this fashion with a argon, let's get that over here, argon number 18, build up 4s2, 3d, 9. We'd expect it to be argon, 4s2, 3d9. Well, that's not. This is a full subshell. You can't fit any more on the S. This is not full or half full. So what copper is actually going to do is shift around some of its electrons so it's got a better arrangement. It's going to take an electron from the 4s and move it into the 3d. So now half full and full. as opposed to originally when it was full and then not full or half full. So this one is much better. It's a lot more stable since we have one full and one half full subshell. Let's take a look at another example and look at chromium. Chromium we would predict based on its place in the periodic table to be argon 4s2 3d4, where we've got a full electron configuration or full subshell and a not full. What it's going to do is make it look like argon, take an electron again from the S and move it into the D. That way now we have a half full and a half full. Okay, which is turning out to be a lot more stable for it. Okay, so it's what it's going to do. Generally, you're going to see that pattern anytime you have 4 electrons in the D block or 9 electrons in the D block. You're going to see those electrons or those atoms kind of shift their stuff around to make sure they have either a full or half full subshell. So let's take a look at copper. Well, we just did it. All right. So it is going to want to be argon 4s2 3d9. It's instead going to become argon 4s1 3d10. Molybdenum here, so this is the 3d, the 4d, and the 5d. We'd predict molybdenum would look like krypton 5s2 44, and instead it's going to look like krypton 5s1 45, half full and half full. Again, you're not going to need to know that for the test, but if you want to go on to AP, it is going to be useful for you eventually. Okay?